Hello, Geography 232 students. Welcome to the 7th week of our class. This week we're going to be looking into DSMs and DEMs, the digital surface model and digital elevation model. And so we will be using a digital elevation model in this week's lab. But before we get to that point, I'm going to talk a little bit about what's the difference between the two and how to create one from a LiDAR point cloud. I'll briefly introduce LiDAR at that point. We'll get into LiDAR a lot more next week and the week after. And we'll talk a little bit about how we can actually use digital elevation models, how we can turn them into actionable intelligence. All right, so this week's agenda, lectures, digital elevation and surface models. This week's lab is map hurricane storm surges. So we're going to use a digital elevation model to map storm surge. Specifically, we're going to replicate the storm surge during Hurricane Sandy, which they call it Superstorm Sandy. And then also, so that's a 3-meter surge, and then we'll also do a 9-meter surge. And you can see how a surge of those heights affect the city of New York. Upon completion of this lecture and lab, you should know how to differentiate between DEMs and DSMs, understand how DEM and DSM are created, and process the DEM into actionable intelligence. We'll do that through our lab this week. Quick outline, defining terms. So I'll describe the difference between a digital elevation model and a digital surface model. I will talk about the data structure. Talk briefly about how to derive DEM and DSM from LiDAR data, and at which point I will define LiDAR as well. Talk a little bit about spatial resolution and scale, and then how do we actually use DEM. So you can derive slope, aspect angle, and contour lines from digital elevation models. All right, first things first, defining terms. Let's get into it. The physical landscape may be visualized via several different methods. You'll hear terms like DEM, DSM, DTM, TIN. These are all acronyms, and they refer to similar but different ways of visualizing the surface. This week's lecture is just going to get into DEM and DSM. And DTM, it's sort of a duplicate term. Digital terrain model is what that stands for. I won't get into that this week, partly because that term actually has two different meanings based off where you're at. In Europe, it's basically the same as a DSM. In America, it's slightly different. It's vectorized, a vectorized terrain model, meaning it uses vector data versus raster. So at any rate, it's sort of duplicative, so we won't get into that. And TIN, a triangular irregular network, it's an older format of surface model as well, and we won't get into that either. So for this lecture specifically, we're going to talk about digital elevation models and digital surface models. In short, a digital elevation model is a bare earth raster grid, meaning a bare earth representation, and a digital surface model would be the bare earth plus natural and built features on the earth's surface. So we'll get into that a bit more. So digital elevation model is a bare earth digital representation of topography. All right, so it's cell-based with a single elevation representing the entire area of the cell. So essentially, the cell represents a single elevation, and it can be anything from sea level on up. Okay, and you might be wondering, can you also take a DEM below sea level? Yes, you can. So that would be a bathymetric representation of the ocean surface or a lake surface, something like that, a lake bottom rather, an ocean bottom. And so, yeah, with a digital elevation model, it is a representation of the surface without any features upon it. So imagine a landscape devoid of vegetation and built features. So no buildings, no trees, just the elevation above sea level. This is used to model hydrology, soils, slope, aspect, things like that. So in comparison to that, we also, or I should say in contrast to that, we also have a digital surface model. That's a digital representation of the physical surface, all that you could actually see with the naked eye. So this displays all surface features, including built and natural landscape. This is surface plus built features. So you would have the elevation above sea level, plus buildings, trees, any sort of natural or built features that are sensed by a sensor, in this case, the sensor being a LiDAR sensor, which I'll get into momentarily. So that's useful in 3D modeling of landscape, urban planning, architecture, anywhere where you need a realistic representation of what is on the ground. Like if you were to stand there in person and look around, a digital surface model would be the closest representation to what you would see. Whereas a digital elevation model is really sort of almost an imagined landscape. It would be what the landscape looked like maybe before development or without any trees, like just like standing in a field of grass, essentially. All right, so what is the structure of these data? Well, this should be somewhat familiar to you. It's raster data, right? We've spent this whole semester talking about raster data, and DEM and DSM are no different. So DEM essentially is a matrix of elevations with a uniform cell size. And so it can be obviously elevation above sea level, which is what it typically is, but it could be something else. It could be elevation below sea level as well. So here we see the numbers. All these numbers represent some sort of elevation. Add some color, a color symbology, and you end up with a raster surface, a surface representing the ground. And that raster surface can be and is usually georeferenced, meaning each one of those cells represents an actual physical location on the Earth's surface. So a cell index number defines a position relative to an x-min and a y-min, an x-max and an x-max, and then the location, the exact location is inferred between those two defined positions. So unlike vector data, where vector data are collections of xy coordinates, right? So if you've got a line feature or a polygon feature, every node in that line or polygon has specific xy coordinates. That's vector data, and that's why vector data is real handy. It can be very spatially accurate and fairly small to create and to share. Raster data, on the other hand, is all about inferred location from a defined xy location, x-min and x-max, and everything in between is inferred. Raster data are projected in some sort of linear units, often meters, sometimes feet if it's in the United States. And so just be aware of that. The spatial precision of raster data is always going to be slightly less than vector, at least at any given inferred location. And that's simply because the definite locations are limited. All right, deriving models from LiDAR. How do we do it? Let's find out. So LiDAR, a brief introduction. What is it? We're going to get into this a lot more next week and the week after. But modern DEMs and DSMs are derived from LiDAR data. LiDAR stands for light detection and ranging. And if you know anything about radar, you know that radar is also about detection and ranging as well. And so LiDAR is essentially taking the same principles as radar, which is sound waves bouncing, it's being sent out from an origin and bouncing off the surface and returning back to a sensor. It's the same concept, but in this case it's with light. And so as you can imagine, as you surely know, light travels much, much faster than sound. And so LiDAR gets to its origin more quickly and more precisely. So we end up with very, very accurate models from LiDAR. So LiDAR systems send a pulse of light from an origin to a surface. That surface can be the bare earth, or it can be the objects on the earth, right? And also that pulse can be a single repeated pulse or a continuous laser wave. And I'll get into this more next week. When the pulse of light bounces off a surface and returns to the sensor, it gives the range, hence light detection and ranging, right? And that range is essentially distance from the origin to the surface of the object off which that light pulse bounces. So the end result is a very large point cloud of elevation values. So every single returned bounce essentially measures the distance from the origin to the surface, and then it creates an elevation from that model. And the height can come from the tops of buildings, tree canopy, power lines, other surfaces, including the bare earth. And because there's so many pulses sent out within a short period of time, we end up with a very high resolution model, okay? And those models can actually be so precise as to be, 1 centimeter resolution or even greater at this point. And as I said, we'll talk more about LiDAR next week and the week after. All right, so this is a example of a point cloud. This specifically is a representation of the Minnesota State Capitol and its surrounding buildings and roads. So you might be wondering, how do we get from point cloud data to DSM and DEM? So digital surface model is derived from LiDAR point cloud. It captures, as I said before, the Earth's natural and built features on the Earth's surface. In the case of a DSM, what we're looking at are actually what we call the first returns. Okay, so and I'm going to get into this, will make more sense next week once we've talked about LiDAR. But because LiDAR is a continuous pulse of light from an origin to the surface, it can actually detect where the first bounce is versus later bounces. And what that essentially means is that we can detect when a light pulse hits the roof of a building or the top of a tree versus when it then hits the ground beneath those features, right? So a DSM is just what we call a first return extraction. Okay, so it's the first return from the LiDAR data versus the surface return, which may be the third or the fourth return. So DSMs are useful in 3D modeling for utilities and telecommunications, urban planning, aviation, and certainly other utilities or other applications rather. You might be able to use it to track where power lines are, where power poles are, track where existing structures are, large structures, small structures, maybe demolished structures. If you're trying to track where, if you're in control of permitting for a city or a county, you might want to be able to know when a residential unit is maybe demolished and then rebuilt. It can be used for that sort of thing. And then aviation, I'll get into that in a second, but essentially you might want to have a clear mapping of what the approach is to a runway so that obviously it's cleared of trees or any sort of obstructions. So because objects extrude from the Earth, DSMs are particularly useful in runway approach zone encroachment, which is what I was just describing. So in aviation, a DSM can determine runway obstructions in the approach zone, and in the case of, we'll say, urban airports, those that are surrounded by buildings, obviously you want to make sure that there is a clear approach so that no accidents happen. Also useful in vegetation management. So along a transmission line, digital surface models can see where and how much vegetation is encroaching. And in my day job where I work, we spend a lot of time in vegetation management looking for potential obstructions from trees and things that might fall onto power lines and spark a fire, right? So DSMs rather are very useful for that, and indeed my organization relies on DSMs for that sort of data. And then finally, for view obstruction. So if you're an urban planner, you might use a DSM to check how a proposed building would affect the viewshed of residences and buildings, or businesses rather. If a proposed, we'll say, skyscraper is to be built in a location, you might use a DSM to see what are the effects on nearby or adjacent structures. Will it block the view? Will it block sunlight at certain times? Things like that. And that information can actually have an effect on whether a permit is granted or if some sort of modification to the plans needs to be made. And here is a zoomed in version of point cloud once again, or a DSM rather, derived from the point cloud. Let's see if we can do it, compare the two. So there's the point cloud, and there's the DSM. And DEM, again, as I said before, instead of being the first return, this would be the last return that actually bounces off of the surface. So digital elevation model is also derived from point cloud data, and that captures only the bare Earth surface. So it's the final bounce of that pulse before it returns to the sensor. And DEMs are useful in perhaps modeling hydrology, soil mapping, and land use planning. So by removing the vegetation and built structures from the landscape, only the elevation data remain. This is useful for hydrologic modeling. So hydrologists might use a DEM to delineate watersheds, calculate flow accumulation, and flow direction, because by stripping out the vegetation, all that's left are the actual contours on the landscape. Soil mapping. So DEMs assist in mapping soils, which is a function of elevation. So as well as geology, time, and climate, soils essentially erode at certain rates based off of the type of soil and the type of geology. And so we can use DEMs to map essentially threats to maybe residential structures on a cliffside, or the effect of a landslide, wildfires, things like that. And finally, terrain stability. So areas prone to avalanches are high slope areas with sparse vegetation. This is useful in planning a highway or residential subdivision. So if an angle is too steep to be safe, essentially we can reinforce a cliffside or a hillside or what have you, and we can use DEMs to determine which areas are perhaps too steep of an angle based off of maybe combining it with the soil mapping, finding out what's porous soil versus imporous soil and where the risks of landslide or avalanche might be greatest. And there's DEM. So compare the two. DSM, this is actually the same locations, and DEM. So this is the Minnesota State Capitol building again, but without the building, right? Well, most of the building being removed. Quick history on the evolution of DEMs. So elevation models were originally derived from what we call stereo photography. And if you know anything about what the stereo means, essentially it was two cameras side by side that took a photo of the same origin point and that slightly offset angle. With that, you could actually put on kind of proto 3D goggles and you could view the landscape in 3D all the way back in the 19th century. So it was a pretty cool, innovative technology at the time. And then that evolved into topographic mapping of contours. So that was essentially created from aerial photography. So once airplanes became commonplace following the First World War, we could see that cameras were mounted on the bottom of planes and aerial photos were taken. And so from those aerial photos, we could derive from the shading of the hills, we could derive more or less approximate elevation or at least contours. Next, we have ground survey. In 1975, the first digital elevation model was created from GPS units, so the early proto GPS units. And if you recall, Landsat 1 was launched in 1971 or 72. And so the early 70s was really kind of the era of the first wide use of satellite technology, right? So we have the first GPS units, ground stations that could then connect with satellites. So we start to get actual digital elevation models at that point, and that progressed up until the introduction of LiDAR. So there's just some real quick screenshots here. We've got topo maps in the 1990s, seamless digital elevation data set complete. So the first nationwide digital elevation model was created for the United States. Elevation derives from national applications, so we continue to increase the detail. In the 2000s, the shuttle radar topography mission was launched, and so that was, as the name implies, a topography mission sensed from the old shuttle, the American shuttle program. And then in the early 2000s, we see the broad spreading use of LiDAR, and that has continued to increase. And now we see LiDAR is not limited to airplane or drone mounted. You can also have LiDAR mounted on the top of a vehicle. And so oftentimes if you go onto, we'll say, Google Street View or Bing Street View, you can see what an area looks like in 3D. And that's because those car-mounted cameras that you sometimes will see from Google driving around your neighborhood, those also include LiDAR sensors. So not only is it taking a photo of your neighborhood, it's also sensing the distance from the street to the structures. And from that, you can combine the two and create a actual 3D representation of all the roads, mapped by Google or Bing or what have you. All right, next, a real brief conversation on scale. So LiDAR-derived DEMs are at a much greater resolution than a USGS standard DEM. So a standard DEM is based off of a 30-meter square area. And so 30 meters square is pretty high resolution if we're talking about like multispectral imagery. As you probably recall, 30-meter images are 30 meters ground spatial distancing, GSD, is what you'd see from the Landsat system, right? So if you're taking an image from space, 30 meters is pretty good because really we use those sorts of resolutions for tracking changes at a larger scale, or a smaller scale, larger area, right? So maybe deforestation, landslide, things like that. LiDAR-derived DEM, much greater scale. So cell size maybe 1 meter, or at this point actually even higher resolution than that. But to give you an idea of how significantly different those scales are, on a USGS standard DEM, we're looking at about 1,600 points per square mile. Compare that to 1.5 million points per square mile in a DEM. And again, that's a fairly low resolution DEM these days. LiDAR-derived DEM. We can find high resolution DEMs that actually have a spatial resolution of 1 centimeter, right? So basically a magnitude higher resolution than what we're talking about right here. And just as a visual representation, you can see that how those two different data sources compare when looking at a 2.5 mile wide kind of swath of land. With the USGS standard DEM, you can make out the river, you can make out that there is some sort of development there, the city of Ada, but you can't make out the various meanders and like there are levees on the side of that Wild Rice River. You can see the little streams that go through the city of Ada. You could make out the different roads that run through the town. So significantly different resolution. So scale determines the resolution, also known as the cell size in this case, and it depends on the source of the data. So older data are going to have lower resolution, newer data higher resolution. Also, if it's an older satellite, it's going to have a higher resolution. Excuse me, lower resolution, and newer satellite will have higher resolution. So resolution determines the use of the DEM and what spatial features are visible. And so if you only need to recognize that maybe there is a river here, or there is some sort of we'll say like a fjord or something, you can do that with a USGS derived DEM. But if you need to find out specifically where are the various tributaries to this river, where and how large of a landslide has occurred, that sort of thing, then you'd want to use a LiDAR DEM. In this case here, it's a 3-meter resolution. So it's the GSD, the ground sampling distance, is 3 meters from one point to the next. DEM and DSM uses. How do we actually apply DEM and DSM to derive actionable intelligence? There are several different ways. So they're useful in determining characteristics of terrain and landscape. So from a DEM, we can derive slope, aspect, contours, and then with a DSM, we can also derive a viewshed, which I mentioned earlier. So what are those exactly? Let's talk about it. So slopes are calculated locally using a neighborhood function based on moving a 3x3 window. So essentially imagine having your entire raster image, and then every 3x3 cell, 3x3 cells moves one little bit at a time, and what it does is it does the math, right? So it takes the difference between adjacent cells, and it subtracts one from the other, and then it divides the rise over the run. So the difference in those vertical values divided by the distance between the points. Okay, so slope is calculated by dividing elevation differences by distance. So if we know what the GSD is, the ground sample distance is, then all we need to do is subtract one elevation value from the next adjacent elevation value, and then divide that by the distance. So if it is we'll say 1 meter resolution, we know that they're 1 meter apart, and let's say one cell A, is at 3 meters elevation. Cell B is at 5 meters of elevation. So 5 minus 3 is 2, so it's a difference of 2, and then it would be divided by 1. So essentially, we know what the GSD is, we know what the elevations are, and that allows us to derive slope. And with slope, we can then identify, how risky maybe perhaps a new development might be if it's adjacent to a very steep hill, or perhaps it's at the edge of a hill and there's a history or there's knowledge of erosion at that location. So slope is useful for identifying how steep an area is and the effects that elevation or that slope may have on development. So when the slope angle equals 45, the rise is equal to the run. That's 45 degrees rather. So 45-degree angle is halfway between vertical and horizontal, or flat and straight up, right? So that's called a 100% slope, and the rise is equal to the run. As the slope approaches vertical, or 90 degrees, that percentage approaches infinity. So the lower it gets, the closer to 0%, and the higher it gets once above 45 degrees, that percentage just continues to go above 100%. So once you get above 45 degrees, you're essentially more down than you are flat. And so that's information that can be derived from slope and is useful for many applications. Aspect. So whereas slope is focused on the angle relative to the ground, so being vertical, straight up, or flat, and anywhere in between that. Aspect is the angle in terms of compass degrees, right, from 0 to 360 degrees. So think about looking down at a compass from 0 all the way around. So aspect identifies the steepest downslope direction from each cell to its neighbor. Think of it as a compass direction a hill faces. So measured clockwise in degrees, 0 is due north to 360 degrees, which is due north all the way again. So 180 degrees would be due south, 90 degrees due east, 270 degrees due west. Okay, so if we combine those two, we can find out both the slope, so how steep an angle is, and what direction it is facing. So at that point, we essentially have a very accurate representation of what the landscape actually looks like. So each value of each cell in an aspect data set indicates the direction the cell's slope faces, and flat areas having no downslope direction are given a value of -1. And lastly, contours. Contours are lines that connect points of equal value. So it may be elevation, temperature, precipitation, pollution, or some sort of atmospheric pressure, something else. So the distribution of lines shows how values change across a surface. So the closer the lines are together, the steeper the angle is. The farther apart the lines are, the flatter the angle is. Okay, so where there is little change in value, lines are spaced farther apart. Where values rise or fall rapidly, the lines are very close together. So that's how we can interpret contour lines. Contour lines are also sometimes called iso lines. So a tight bunching of iso lines or contour lines means it's a very steep angle. So maybe it's mountain range. Very far spread apart lines means it's very flat. So maybe it's a basin or a prairie or something like that. Okay, so that's how that works. And all those can be derived rather from digital elevation models. Okay, so I believe that sums up this week's lecture. Feel free to reach out with any questions via email or on the discussion board. And we will chat about this week's lab at our meeting. And until next time, have a good one. Bye-bye.